Hello friends, welcome to the online lecture series of St. Andrews Institute of Technology and Management, Gurugram. Myself, Satinder Vats, Assistant Professor in ETCE Department, and our today's lecture is about Z transform, which is in Unit 4th in the subject Signals and Systems of Branch Electrical and Electronics. Today we will see how we can find out the causality and stability of an LTI system using Z transform, and we will see how we can solve the difference equations in Z transforms. Okay, so let's start. So we have already learned about the Z transforms, inverse Z transforms. In this part we will see the causality of LTI systems. So an LTI system or a causal LTI system has an impulse response Hn, that is 0 for n less than equal to 0. That is, what do you mean by n less than 0? That is, the system is a right-handed signal. The value of the signal for n less than 0 is 0. That is, in the left side of the y axis it is 0. We would get only values for n greater than 0. That is, in this part of the system we would get the value of our impulse response Hn. If impulse response of a system is such that Hn is 0 for n less than 0, then the system would be causal. Alright, so first point is, a discrete time LTI system is causal if and only of the ROC. ROC we have already learned in the previous lectures. ROC of its system function is the exterior of a circle including infinity. We have already seen that ROC in Z transforms forms a circle like that. If this is the real and imaginary axis Z plane, if it is the Z plane, then ROC would be something like that. It would be inside the circle or it can be outside that circle also. Okay, so we have to find out the causality of the system. For that we need to check the system function Hz. For an example, let's say if we are given Hz, which is the basic Z transform formula as well. If we are given Hz is equal to Hn into Z raised to power minus n summation 0 to infinity, as the signal should be a right-handed signal, so it does not include any positive power of Z. That is, the ROC includes infinity and will be outside of a circle, so it would be something like that, outside a circle. If the ROC comes out to be like that, then the system would be causal. Okay, and second point is, if Hz is rational, that is, we are given a function Hz which is a rational function, then the system to be causal, for the system to be causal, the ROC must be outside the outmost pole. If we have two or more poles, okay, if we have, this is our Z plane, if we have one pole over there and second over there, so there will be two rings like this. Okay, so our ROC should be outside the outmost pole, so this should be our ROC for the system to be causal. For the impulse response to be 0 for less than 0, the time value of time less than 0, it should be 0. It is possible only if the ROC is like this, outside of a circle. Okay, so a discrete time LTI system with rational function, we are saying the function should be the hz function, that is the system response function, should be rational function. Okay, a discrete time LTI system with rational system function sz is causal if and only if first the ROC is the exterior of a circle, that is the ROC should be outside of a circle. Okay, like this. And second, the hz expressed as a rational polynomials in z, the order of the numerator cannot be greater than the order of denominator. That is, if we are given a function sz like this one in this example, if we are given this one, sz is a function, rational function with numerator and denominator. So as we have seen in the definition over there, the order of the numerator cannot be greater than the order of denominator. Okay, so in this example, order of numerator is greater than, it is 3 for numerator and 2 for denominator. So this function or this system is not causal, because if the numerator has a greater power, then what would happen? Hz will not converge. So for that to hz to converge, that is at z that is at z, when z tends to infinity, h of z must be a finite value. It must be a finite value. But if the numerator has a greater power, then it is not possible. So for a system to converge or to be causal, the denominator should have a higher power than numerator, or numerator should have a lesser order than the denominator. Okay, so in this example we can see the numerator has a greater power, so it will be non-causal. Let's see one more example. In this example, sz is given as a addition of two different function, 1 upon 1 minus 1 by 2 z inverse plus 1 by 2 1 minus 2 z inverse. We are given that the ROC is z greater than 2. So we need two conditions. First condition is fulfilled, that is ROC is outside of a circle. Okay, ROC is outside, it is 2, as we are given z is greater than 2. So ROC would be this, outside of this circle in this second example. Okay, so and second condition is the numerator of the polynomial must have lesser order. So here we can see, if we simplify the expression, what we get is this one. So both have the same, it should not be greater, the power of numerator cannot be greater, it can be equal. So both are same, the system is causal. So this is how we can find out whether system is causal or not, using the ROC and the system function. Okay, now let's move to the stability. So how can we find out whether a LTI system, that is a linear time invariant system, would be stable or not? We can find out using the system function itself. So there are two conditions: an LTI system is stable, an LTI system would be stable if the ROC of the function includes the unit circle. That is, if the ROC includes this circle. So it should be of the form ROC must be like that, it should be like that. Okay, so this ROC includes the unit circle, so it will be stable, or it could be like that also. Let's see. if we have the unit circle, so ROC could be like that also. If it is inside the circle, it also includes the unit circle. So in this case also it would be stable, but it would be non-causal at the ROC is inside the circle, as we have seen earlier. Okay, so we can tell about both the things, whether the system would be causal and stability using the ROC and the system function. The second condition is if a system is causal, that is a causal LTI system with a rational system function Hz, is stable if and only if all the poles of Hz lie inside the unit circle, that is they must all have magnitude smaller than 1. So poles, that is all the poles must lie in the, these should be the poles. Okay, they must lie inside the circle, so the ROC would be like that, and it includes the unit circle. For that to happen, the let's see the example first. As we are given Hz is equal to 1 upon 1 minus Az inverse, that is z upon z minus a. So this function has a pole at z is equal to a. So if a is less than 1, if this a is less than 1, the unit circle, it would lie in the unit circle. If a is less than 1, this pole would lie in the unit circle and the ROC would be like this. So it will be stable. So value of a should be less than 1 for the system to converge, system function to converge, or the system be stable. Okay, so now let's to move to difference equations. So if we are given linear constant coefficient difference equations, so we can use the properties of that transform to analyze these systems for system function, frequency response, or time domain response. So time domain response is denoted by h of n, whereas the frequency response is nothing but the response in z domain. Okay, and the system function is hz itself. We will see how we can use that transform to convert the difference equation in algebraic expressions. Okay, so let's see, let us understand it by an example, because it is the best way to understand these sort of equations. So here we are given a difference equation yn minus 1 by 2 yn minus 1 is equal to xn plus 1 by 3 x n minus 1. So all of you can see that what is yn minus 1 in this equation. Yn minus 1, that is yn minus 1. What is this? We have already seen, learned about this signal in the first unit itself. So yn1 is nothing but a time shifted version of yn. It is a time shifted version of yn, or most precisely it is the delayed function by unit 1. So we have already seen in the z transforms that if let's say yn is the function, its transform would be yz. Now if we time shifted it by 1 unit, then the z transform would be z minus 1 of yz. Okay, this is a time shifted function. So in that transform there will be a multiplied term z raised to power -1. So this is how we can convert this equation, difference equation, in the form of z transforms. Let's see how. So here this equation, taking Laplace transform on the right hand side and left hand side, what we would get, yn would become yz, this term would become 1 by 2 z inverse yz, as yn is shifted by 1 unit, so there is a delay of 1 unit, so we have z raised to power -1 in the equation. Similarly for xn, the transform is xz, and for x minus 1 it is z raised to power -1 into xz, because it is also a time shifted version of x of n. So rearranging the equation, we get yz is equal to xz into 1 plus 1 by 3 z minus 1 divided by 1 minus 1 by 2 z inverse. So as all of us know, what is hz? Hz is nothing but yz upon xz. So rearranging the equation, we get hz as 1 plus 1 by 3 z inverse divided by 1 minus 1 by 2 z inverse. So using that difference equation, we have calculated the system response as h of z. Okay, so from this we can calculate the response in time domain, that is h of n, using inverse z transform. So we are given that hz is equal to 1. Rearranging the equation, we get hz is equal to 1 upon 1 minus 2 z inverse and plus 1 by 3 z inverse. So as we have already seen in the inverse z transform, the inverse z transform of this function would be this, a raised to power n un, where a is equal to 1 by 2, and this function is a delayed function. So we will get a is equal to 1 by 2 in this equation. 1 by 3 is a constant, so 1 by 2 raised to power n, and it is a delayed function by 1 unit, so we will get u n minus 1. Okay, and similarly we get the power of 1 by 2 as n minus 1. Instead of n, we will get n minus 1, because it was a delayed function. So this is how we can calculate the system response in time domain. So next topic in this lecture is block diagram representation, how we can represent a equation or a LTI system given in difference equation, or if we are given the system response, how can we represent our LTI system using block diagrams. So we can represent a causal LTI system, okay, described by difference equation using block diagrams as well, which involves basically 3 operations. Okay, so it for to represent the system using block diagrams, we need 3 operations. So first is addition, second is multiplication by a coefficient, and the third one is unit delay. That is, if it is a delayed function, then we see how can we draw the block diagram. Let's see with the understand with the example. We are given that a causal LTI system with system function sz. We are given a system function hz, which is nothing but the ratio of output in z domain divided by input in z domain, that is yz upon xz, and it is given to us as 1 upon 1 minus 1 by 4 z inverse. So rearranging the equation, what would we get? Rearranging this equation, we get, okay, rearranging we get xz is equal to yz minus 1 by 4 z inverse yz, or if we want to move the yz, that is the output, on the other side, we can rearrange this as yz is equal to xz plus 1 by z inverse yz. So we are in this equation, what we have, yz, that is the output, is depending on the input xz, okay, input xz, and also on the delayed version of output yz. So we will need a feedback path in this, because the output yz is depending on the input xz, or we can say xn, and also on the time shifted version of yz, because this results in a time delayed function, that is it would be yn minus 1. If we take inverse transform, it will come out to be yn minus 1. Let us see how. So if we take inverse z transform yz, it would become yn. For xz, it would be in x n. For yz, it would be yn, and this would be yn minus 1. So we have calculated the inverse transform and represent the equation in time domain. Okay, here you can see we have represented the equation in time domain. So yn, that is the output, depends on input xn, okay, input xn, and the time shifted version of output, that is we need to have a feedback in that. So let us see how we can draw the block diagram. So here is the input xn and here is the output yn. Yn depends upon summation of input xn and the feedback path, which is used to define the time delayed function or time shifted version of yn. So how we can get the yn? It is the summation of xn plus yn minus 1. So yn xn is there, we have a addition, as we have already seen. We need 3 operations: addition, multiplication by constant, and a delay of unit 1, which is represented by z of minus 1. Okay, so how we can draw? This is our input, this is our output, this is the multiplication term, this is delay. So here two terms are added, xn, that is this one, and 1 by 4 yn minus 1, which is denoted by z inverse. So 1 by 4 is the constant which is multiplicated in yn minus 1, and yn minus 1 is represented by a delay z inverse. So this is how we can draw our block diagram. Let us understand with one more example, try to understand it more precisely. We are given, okay, here we are given h of z as this one, which is a rational function, 1 upon 1 plus 1 by 2 z inverse multiply by 1 minus 1 by 4 z inverse. So which comes out to be, if we expand it, 1 upon 1 by 1 plus 1 by 4 z inverse minus 1 by 8 z inverse. If we convert it into the time domain using inverse transform, what will we get? Yn is equal to minus 1 by 4, because here we have 1 by 4 z inverse, so it would be minus 1 by 4 yn minus 1. When we take it to the other side, it becomes minus, and this sorry, 1 minute. So this 1 by 8z has 2 units of delay, that is z raised to power minus 2. It has delayed of unit 2, so it would be 1 by 8 yn minus 2, and xn would be xn. So yn is a function of input xn plus the time shifted versions of output, that is yn minus 1 and yn minus 2. So it can be represented by two forms, that is direct form and the cascaded form. So in direct form, yn is equal to the summation of x1, that is this one, and two functions which are time shifted by 1 unit. This one is by 1 unit and this by is by 2 units. Okay, so how can we represent them? There is 1 unit delay, and if we add another block of z minus 1, it will be 2 unit delayed. So for first we have 1 by 4 yn minus 1, so we will multiply by a constant minus 1 by 4 in z inverse, and for second we take another block for a delay of minus 1 unit, and the multiplied by it 1 by 8, so it would be this one. So all these terms will be summed over there and will give us the output yn. So what we need to do to get the block diagram? First calculate the system function. Okay, first get the system function. If it is not given, get the system function, then convert it into the time domain, or with some knowledge of inverse transform, we can also convert it directly with the system function, but for the time being let's convert it into time domain. So here we converted it into the time domain, and we will see how many terms are shifted by 1 unit and how many are by 2 units. Similarly we put the our blocks. Okay, now it can also be represented using cascade forms, that is both these parts can be used one after another. So in first part of the upper part we have 1 unit delay, so we describe it here, z inverse multiply 1 by 4. Now if we want in second function, in this function, another unit of delay, so we add one more z minus 1, and since we have multiplied it by 1 by 4, we will take minus 1 by 4, we will take 1 by 2, so both of them get multiplied and it would become 1 by 8. Okay, it would become 1 by 8 into z raised to power minus 2. So this is how we get the cascaded form. So I hope guys you understand the z transforms. So this is it for the lecture. See you in the next lecture.